So we first asked, what's science? And someone came up with a good answer saying that it's about repeating experiments over and over again. And then I also said that it has to do with the idea of a theory. And do we think that there's a theory that is a kind of underlying rule that explains the phenomena? And then if there's a theory, then even though there's a theory, we expect that when we look at data in the real world, we won't find that the data follows that theory perfectly, but rather that there's going to be some sort of what we sometimes call error off of the model, where the model has some error. The theory doesn't have some error, but it doesn't predict the data exactly, and so we say there's some error in between the data and the model. So we talked about that, and we looked at that, some objects falling, and we talked about the physics law that supposedly governs those objects. And then we started to talk about neural networks, and we talked about the input variables. Those are also called explanatory or predictors, and the output, sometimes called the response variable. One advantage of a neural network is that it's not linear, so it can express very complex relationships between the predictors and the response. So it's not just like a simple straight line model. And this comes from this. Just let me fix this. The person, I guess, who developed the idea of a neural network modeled it after the neurons in the brain, and there's some input and there's some output. So in the same way we have in a neural network, we have some input. We transform that input in some way. Remember, this is the sigma that you just had the quiz on, and then this is the activation function. And in the quiz, you just had a very simple activation function. Here, we're talking about maybe this kind of S-shaped function. This would be like it's probably a logistic curve. And anyway, whenever we do something in here, this is usually referred to as the black box. Okay, because we don't really know what's going on in here. We just put in the inputs, and the algorithm spits out a prediction. And inside, we don't really know what's going on. And even if we can see what's going on, we don't know how to interpret it. There are other models, other ways of doing these kinds of predictions, where you can interpret the model itself, but with a neural network, we don't try to interpret the model, we just try and use it for its outputs, okay? Like in regression, when you do regression, I don't know if you've studied regression, but regression is a classic technique, and in regression you can say, oh, this input variable has this much importance in making this prediction, and this input variable has that much importance in making the prediction. So you can weigh how important the inputs are, and you can talk about their value in terms of predicting the output, or how much effect they have on the output, but you can't do that here. So this is, again, referred to as like a black box. Okay, the inputs xi are collected from upstream neurons, or the data set. So here it's the data set, and combined through a combination function, such as the summation, we just talked about that, which is then input into a usually nonlinear activation function, which is this S-curve, to produce an output response y, which is then channeled. So they keep going. In our pictures, we only had, I think, a single, what's called a hidden layer, but you could have many hidden layers. So here they're being general and talking about the fact that you could go through many hidden layers. And here we had a data set, and we had, this was about cheese and whether people liked it or not, in terms of, and we used input variables of fat and salt content. So those are our two predictors, fat and salt. And here's a picture of a neural network. And in this picture, there's just one hidden layer, but you can set up many hidden layers. Like in Weka, you can set up many hidden layers. You can decide how many you want. And that will add to the complexity of the model, that will add possibly to its effectiveness, but it could kind of mess up its effectiveness because, well, we'll talk about why adding too much complexity can be a problem. But so the question is, can you add just the right amount? That's hard to say what that means. There are no rules about it. Okay, anyway, in this case, we just have one hidden layer. And in that hidden layer, by the way, you can decide how many nodes you want to have. So here we have 5, but you could have 2, you could have 20, you could have 100. Okay? So, and the way you set it up seems to have some effect on the predictivity or the accuracy of the model. But there's nobody who can tell at this point. There's been not enough research done to say, oh, it should be done this way or that way. In fact, there's probably no hard and fast rules at all. Okay, so here we have the neural network for the fat and salt and the acceptance. We looked at that and we talked about it. We talked about this and all this, this. And we said we're going to use this kind of function, which you just had a quiz on, to sum up what gets put in here, gets multiplied by these weights, gets sent into here. And then the next step is, after it's sent into here, it's sent through the, what's that function called again? Anybody remember? The function, the logistic curve, do you remember the name they use? That, it can be lots of different functions. Could be the logistic curve, could be a linear curve, could be a blah, blah, blah. I think we said it could be an exponential, but in general, what do they call it here? What? Activation, called the activation function. And actually, I don't quite, maybe I can discuss why they call it activation, but right now we'll just say it's called the activation function. Okay, so we saw this, and like we said, we're going to put the summation into another function. In fact, that's the activation function. So we're going to put the summation stuff into the activation function, which is what I said here. So we're going to take all the summation stuff and put it into G. What kind of G would that be? So it has to be what we call monotonic. So that means it can be either decreasing or increasing, but not both. So this is okay, that's okay, this is not okay. This is increasing, that decreasing, that's not good. We don't want that kind of function for the activation function. Okay, so g of x can be any monotonic function. In math they use monotonic. So these are all examples of monotonic functions, linear, exponential, logistic, but it doesn't have to be one of those. And you know what linear means. And the exponential is a function like e to the x, for example. It doesn't have to be e here, it could be any number here. E is a number, it could be any number, but that's an example. Or it could be like this, a logistic curve. And we said it gave some reason for why a logistic curve might be good, and this seems to be important in a lot of different fields of study these days. Everybody's using and talking about logistic curves. I guess, and for example, we have Professor Asagari, Baruza Asagari, and he teaches like operations research and some other subjects related to that. He does a lot of research that involves this curve. He does research in technology diffusion. Technology diffusion means when new technology enters the world, enters our life, how quickly does it get accepted? What happens, what's the acceptance rate, how quickly? And so this S-curve actually is a reasonable model for that, because what happens at first, this is the amount of the percentage of the population that has started to use the technology. So what's the idea? First it grows slowly, then it starts to grow very quickly, gets adopted by a lot of people, and of course then it tapers off in its adoption. So this describes that kind of phenomena. And there are lots of other phenomena that seem to follow this kind of shape. So people are very excited about logistic curves. Okay? But in our case, we might use it as well. But in any case, it just has to be a monotonic function. This curve is also monotonic, right? Is it decreasing ever? Does this curve ever decrease? No, it doesn't, right? It's always increased. It doesn't increase at the same rate all the time, but it's always increasing. Okay, so our logistic curve looks like this because we take our summation here that we had a quiz on, we put it in the logistic curve, but the equation for the logistic curve, I forgot to write that part, but it's this. The basic equation for it is, like, let's say call it L. L of x is 1 over 1 plus e to the minus x. That's the basic form of the logistic curve. So instead of putting in x, though, we're putting in our sigma stuff, right? So we put in our sigma stuff, and that's what you get on the right-hand side of that equation. Right? Understand that? This is logistic curve. Hopefully, is this always increasing? Let's see. Let's think about it. As x gets bigger, let's say x goes from 10 to 20 or something. So what happens to this? So when x is 10, we get what? We get e to the minus 10, right? So what's that? That's 1 over e to the 10, right? And then what do we get when x is bigger than that? 1 over e to the 100, right? So this versus this, what's the difference? This one is smaller, right? Right, 1 over a big number, 1 over a not as big, so this one is smaller. So we're adding a smaller number here, so this is bigger. Right? If you're adding a smaller number here, then 1 over it is going to be bigger, right? So it does increase, right? At least for those two numbers it does. So that's the idea of the logistic curve. Okay? Everyone follow what I just said? Okay. So, fine. Okay, going back to our example, we need to set the values of w. So what was the rule about that? How do we set the w's at the beginning? Because, okay, the idea here is that we have some w's. Remember, these are the, let's see, this is the picture, right? Here, let me make it bigger just for a minute. No, I don't want to do that. Anyway, you can see the w, all these w's, right? Okay, so how do we set those? So the idea is we set these w's, we put our data in here, we get a number out here. It's supposed to predict whether the consumer accepts or not. So how do we set these w's at the very beginning? What did we say? Okay, I said that we set them at random, which sounds preposterous and stupid, but that's because what we're going to do is we're going to set them at random, but then we're going to adjust them later. So each piece of data that we run through, it's going to have some error, then we're going to sort of use that error to reset the w's, maybe so that they'll improve their predictivity. Is that a word, predictivity? I'm not sure. I'll make it up right now. Predictivity. I'm not sure if that's a word or not. Anyway, well, their predictability, I guess is the real word, predictability. So we'll improve the predictability of our model here by changing the w's somehow. But we don't know how to change them. But we'll learn how to change them. But the thing is, we have to start with some w's. So we just set them at random at the beginning, acknowledging, of course, that it's not going to be good at the beginning, but later it will improve. Okay? So set them at random, usually small and in the range from 0 plus, somewhere in the range of 0 plus or minus 0.05. Okay, so we set them like that. So we could try W1, 3. Remember, what does 1, 3 mean? Starts from node 1 and goes to node 3, right? So we're setting this one here to 0.05, and we'll set the 2, 3, which goes to here, to 0.1 as 0.01. Using the logistic function, we can compute the output of node 3. Okay, so this is what goes into node 3, and then this will be the output for node 3. So the output of node 3 is 0.43. Does everyone get the idea here? Is this clear? I didn't run this. Is that clear? Right? This is what you got quizzed on here. And then we put it into the logistic function, so that's what comes out. Okay? All right. So here's all the values. Da, 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 da. So when we put in this value for fat and this value for salt, apparently after you do all this stuff, what you get out is here, 0.506. Okay, now you should be confused. You should say, what do you mean 0.506? We're supposed to be predicting whether they're going to accept it, whether the cheese is acceptable or not. And I get 0.506, what does that mean? Right? You could be confused, somebody could be confused whether you are or not, I don't know. But maybe you can help somebody else. What does this mean? Or how do we use this? 0.506, explain that to the confused person. No? Anybody? Okay, so it's 0.506, right? Will you say, what? It's actually not probability, but that's a reasonable guess. But actually, it's not that. Okay, but it's something like that, because what it is then we just make an arbitrary cutoff value. So we say, if it's above blah blah blah, maybe if it's above 0.6, then we're gonna say that it's acceptable, and if it's below 0.6, we're gonna say it's not acceptable. Okay, so we use a cutoff value when we have a so-called binary response variable. What does that mean? Binary response variable. First of all, what does response variable refer to? That's the output variable, right? The output variable. So what is the output variable in our example, in this example? What is the output variable? What are we trying to predict? Output variable means what you're trying to predict. What are we trying to predict with this data? Yeah, whether they're going to accept or not. So that's the output variable. Now, is that a numeric variable, acceptance, non-acceptance? Not really, right? Right? You wouldn't say like 20, right? Doesn't really mean anything, right? It's just yes or no, right? So it's binary. So it's a binary response variable. Okay? Okay? So what does it say for classification? So, this word classification in data mining is very important. It's classification versus, now I probably use these words incorrectly most of the time, because I've been using the word prediction. It's not, what we're doing is actually not technically called prediction. Okay, it's called classification, because prediction means the output is numeric. That's the technical definition for prediction. So if you're trying to predict the temperature, that's okay because temperature is number. But here we're not trying to predict a number, we're trying to predict a yes or no. Right? So they don't call it prediction. They call it classification. We're trying to classify, is it yes or no? Which class is it in? Okay, so they call it classification, but I may use the word prediction incorrectly all the time. Okay, because that's just what comes out of my mouth. Okay, so this is actually a classification problem. It's called, in data mining, it would be called a classification problem. So when you're doing classification in a neural network setting, which this is, a neural network setting, but in neural network, you're gonna get a number out here. You're not gonna get a class, you're gonna get a number. So you have to set a cutoff. If the number is bigger than something, you use one, you say it's one class. If the number is less than that something, it's the other class. Okay, does this make sense? Okay, so that's the language, and that's the way we use that language. Okay, so and if you, anybody have any suggestions for what you could do if you didn't have a binary variable? Maybe you don't just have yes or no, but you have like, let's say, really like it, it's okay, and hate it. Then how do you set that up? Anybody, or how could we set that up? You know, you can kind of make it up on your own. How could we set that up? What would you do? You get this number out, what would you do with it? So far we said, okay, maybe if it's above 50, then we're going to say yes, and if it's below 50, we're going to say they didn't like it. But suppose we wanted to have a 3-class output variable, like super good, medium, and terrible. So how could we arrange that here when we get this output? Kind of natural thing to do would be what? Say, well, like if it's above 70%, if it's above 70, then super. If it's between 70 and 40, then okay, and less than 40, it's not, right? It's obvious, right? And that's what they do. Okay, so they say, oh, there's another way to do it, I'm sorry. No, there's another way to do it. That's one way to do it. There's another way to do it, which I won't explain right now, but here it's written how to do it the other way. But I don't want to confuse things right now, so I won't mention that at the moment. So the output at node 6, the final node, is 0.500. To classify the record, we use the cutoff of 0.5, but it doesn't have to be 0.5. You can set it to be what you want and obtain the classification into class 1 because 0.506 is greater than 0.5. So what does this mean? Remember, we have just run our first observation through the network, right? We only ran one observation through our network so far. Okay, so what does it mean? We just said that in the last slide, to classify this record, we use the cutoff of 0.5 and obtain the classification into class 1. So it means that we are predicting that the first cheese sample was acceptable, right? Right? Everyone get it? So we've made a prediction that the first one was acceptable. Okay, now we need to train our model. Training the model means estimating the thetas and the w's. Where are the thetas in this thing? This picture, the thetas were where? Oh, these. We kind of skipped over the thetas, so I'm going to continue to skip over them for the time being. So we won't worry about the fact that we have to train the thetas. They're just other part of what we have to train. So anyway, we have to train, let's say we have to adjust our w's so that they lead to the best predictive results. So we started with random w's, so we certainly don't think we're going to get good predictive results at that point. Right? It would be, you know, we certainly don't expect that. But we ran one record, one cheese, through our model, and we might have predicted correctly that it was acceptable, or we might have predicted incorrectly that it was acceptable. We decided that we're going to say that it's acceptable. Right? Why did we say it was acceptable? Because it was above our cutoff value. Right? So we decided we're going to say that it's acceptable. That doesn't mean it really was acceptable. In fact, we can go back and check our data set to see what it actually was. It was acceptable, actually, but that's just like almost a coincidence at this point. Because we did just have random w's, so there's no reason to believe that our model is any good at this point. But we did predict that it was acceptable, and it turns out that it actually was acceptable, but that's just a coincidence at this point. Now what should we do, though? Now, suppose that we got it wrong. we predicted that it was acceptable, but it wasn't. And what we want to do is adjust our W's somehow. Okay, and that's the topic for our class today. Okay, how do we adjust the W's? Okay. Okay.
Does it mean that we change the connection?
Oh, let's see. What's that? Okay, here. Sorry.
Lines? Do we change these lines? How do we?
Not the lines, because the lines are, no. We're going to change these W's. Remember, first of all,
Values.
what?
Values?
Yeah, the values of the W. Yeah, sorry. The values of the W. Like, where did this 0.05 come from? That's a trick question, because it just came at random, right? And where did this come from? That was also at random. All this stuff was at random. And we have no reason to believe that at this point we're going to have any good predictability. That's the right word. And actually it's the wrong word, because we think that our model classifies well, right? At this point. So we get it wrong, then we want to say, oh, I want to change these somehow. But the question is how? How can we change the W's so that maybe the next time they'll do better? Okay, that's a hard thing. I mean, somebody was a little bit, well, maybe I should say, this theory grew out of some other stuff where they worked with similar questions, and maybe they employed the ideas from other areas to come up with this idea. But it's weird. It's hard to imagine. I mean, what's just the basic intuition here? How could we possibly figure out how to adjust these? Does anybody have any idea?
I guess first we have to decide what kind of
I mean, before you answer, there are probably a lot of ways to do it. So you might not guess, of course, the way that they finally decide to do it. And the interesting thing about that is that you could write your own code that will maybe come up with another idea, and it might work. But go ahead, sorry, what were you going to say?
Then, like, first we decide which kind of outputs are correct and incorrect, and after that we put it into the equation and like kind of like chase down the part that was wrong, and then put a new number that is close to it.
Oh, wow. That's really great. I don't have such good intuition, actually. I had to think about it and read what they did because I didn't really see how to do it. But that's basically kind of what they're doing. Okay, but anyway, it's complicated. But yeah, that's the kind of idea, I think. So, anyway, so the idea, as we've said, is that we need to somehow adjust our W's to get better predictability or classification results. Okay? We repeat the process for all the cheeses, 1 through 6. For each cheese, we compare the prediction to the actual value. Then we proceed to back propagation. So that's the way it's done. The name of how it's done is called back propagation. Here's another language that if you're going to study neural networks, you'll probably want to know this word. This is called fully connected. So fully connected just means that if you check any node, it's connected, there's a line from it to every previous node. Every node in the previous layer, I should say. Right? So if you look at this node, it is connected to every node in the previous layer. If you look at this node, it is connected to every node in the previous. But you don't have to set it up that way. You could set it up differently. Okay? But this is called fully connected, and this one is also connected to the ones in the previous layer. So, as I said, you can configure these things in a zillion different ways, an infinite number of ways, I guess we could say. And nobody knows which is going to produce the best results in terms of getting the predictions right at the end. Okay? So this is called a fully connected feed-forward neural network. And the reason feed-forward means that we're sending stuff in this direction. from left to right, I guess. But as I said, we're trying to figure out how to adjust the weights, and that's called backpropagation, or the answer is called backpropagation. It's based on something called the gradient descent method of optimization. So like I said, this theory of gradient descent comes from the general research of optimization, what's called optimization theory. Okay, so there's something already existing before they were working with neural networks called gradient descent, and somebody just said, hey, let's use that in this neural network problem. Okay, and this is a reference to maybe where this comes from, 1986, not too long ago. The principle of operation of the backpropagation algorithm is quite simple. First, the inputs from the training data, that's what we've been doing, we just took all the inputs from our cheese data set, are propagated through the network to the output. The model outputs are then compared with the actual outputs. That's what we said, we're going to compare our prediction with the actual data. Whether in this case, was it acceptable or not, the cheese. The difference is the error. So we get some error. Sometimes yes, sometimes no. But sometimes we get it right, sometimes we get it wrong, so that's the error. This error is then fed backwards into the network, and the connection weights are adjusted. So that's exactly what we've been saying, nothing new. Okay, here's an example. Suppose we have the network given above. So we saw that network, here it is. Node 1, node 2, node 3, node 4, node 5, node 6, 6 nodes. Suppose we have that, then we have these weights, right? 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5, 4, 6, 5, 6. Is that right? Yeah. 1, 4, 1, 5, 2, 4, 2, 5, and so on, right? We have those weights. And we have the arbitrary weights here. So this is the random setting. So node 4, we were just quizzed on how to calculate what goes into node 4. So here it is. So we get a value input of 1.64. The output from node 4 will be gotten from the activation function, which is this logistic function. So we're going to put this number in here. K is a constant. You set that just like you can set the number of nodes to any number of nodes that you want. You can also set this K to any K you want, and then just try it out. Right? See if you get good predictions or not good predictions. Okay, but anyway, this K is just a constant. Okay, similarly, the input into node 5 and the input into node 6. So we can do all these calculations, and we won't bother with them. We'll just accept that those are the correct numbers. Now suppose that the actual output from the final node 6, this is the final node, the actual output, this is no longer cheese anymore. This is just some data that we don't know particularly what it's about. But the actual value for the output is 0.6. So how much error did we have? We predicted what? 0.7153, but the actual value was what? 0.6, so there was some error. Right? How much error? Was this number minus this number, which is this number? Okay, so we got some error. Now the question is, what do we do with it? How can we use it? How can we adjust the W's, all those different W's, based on this number, based on this error, 1153. Now, can you say your idea again? It sounded right, but I don't quite get what you were saying.
Me? That first we decide which kind of outputs are right and which ones are wrong.
Okay, well, no. In this case, the actual value is 0.6. That's the real number that we're supposed to get, but we actually got this number. So this is our error. So what do we do with this now?
Then somehow we need to
Use, okay, which equation? Like all that,
The hidden layer.
okay,
that
okay.
changes the data.
Yeah,
Somehow in there we have to like put this error in,
Mm.
like chase down which parts of the input layer were wrong, or like
but how do you even, how do you mean wrong? And well, inside, in the inner layers. Because I was thinking about that too, I was trying to think about it. You don't have any, the only place where you can measure right or wrong, these stuff here, there's no, nothing in our data set about this stuff, right? Our data set is about these inputs and this output, and that's all, right? So we don't have any, I mean, we just don't have any other stuff but that, right? So we can measure wrong right here, but how do you measure wrong? What do you mean? What does wrong mean in here? We don't even have any data there. We have data here, but that's not what we're talking about. We have data here, but I'm talking about inside. So how do you even measure wrong? I don't get what you're saying exactly.
to get an output from input, we need to use some kind of an equation.
Yeah, that's right. There is an equation here, and it's a pretty complicated equation. Can you understand why I called it why it's pretty complicated? Okay, let's think about it. I'm saying that this whole neural network is a predictor function. So let me give it the name, what should I give it? I'll call it C, because it's let's say it's a predictor function. So I'll call it like a big P. Okay? And it takes our inputs and predicts an output, right? And we don't have just one input, we have a couple inputs. Like in this picture, we have 3 inputs, maybe. Input 1, input 2, and input 3. So let's call them x1, x2, and x3. So it takes those 3 inputs, and it's going to make an output, right? Let's just say it's, okay, that's good enough. So it's going to make an output, let's call it y. Okay? So it's going to make an output. Now, what's the notion, what's the nature of this p function? Or what is the equation for this p function? I claim it's pretty complicated. Because, what do we do with these x1, x2, x3? We have to do that sigma into each node, and then do the logistic on each node, right? And it's going to be pretty messy to write it here. It's going to be very messy. It's going to be like, I guess it's going to be like this, actually. It's going to be equal to, the last thing that we do is what? When we output, what's the last thing we do? In other words, from node 4, what do we do? Oh, no, sorry. From node 6, what do we do? How does node 6 output? It uses the activation function, right? Right? Every node uses the activation function to output, right? So it's going to be like this, basically. 1 over 1 plus e to the minus something, right? But this something is going to be a horrible thing because it's going to have in it, well, we could say it's going to have the sigma from, it's just going to be horrible. I'll just leave it at that. I'd like to see it written down somewhere, but I don't want to try and write it myself, actually. It would take a long time. So it's going to be really, really messy. Okay? But anyway, we can just express it very simply like that. Right? But it's a really horrible thing when we try and write it explicitly. Okay, so how do we propagate the error backwards? So anyway, you had a good idea. What did you say? You said, oh. Well, anyway, let's go on with it. Let's go on with the discussion. So how do we propagate this error backwards? The error is 1153.1153. It means how should we correct W46 in light of the fact that there's some error and we want to fix the weights, fix them, help them to possibly reduce the error for the next time. Right? That's what our goal is. We ask, what is the error W4, 6? What is the error in W4, 6? So that's like a weird question. It's like, there's not a right answer, but we're going to try and give an answer and adjust, and then make adjustments in W46. Another notation for that is this, the error in W46. Not a much. So there's an error of that. How do we propagate this error back? Sorry, I did that already. Okay, now I'm going to shift to this book. So, all right, we got to that question with the previous problem. Now I'm going to shift to this book, which you can find, if you like. There's, I think, chapter 6 in here is on neural networks. And he's using this, this neural network, which is a little different than the other one, but so much, just another neural network. Maybe it's the same one, but different names. Okay? So node 1, node 2, node 3, node A, B, no, it's not the same. He didn't, in the last one we didn't use numbers and letters, but okay, so this is what it is. Okay? And now we're going to have different data inputs. We're going to have these 4. Now you might be confused and say, wait, there's only 3 nodes, but if you look here, how many input values are there? 4, right? So that's obviously doesn't make sense. But just a technical thing, which I'll explain later maybe. It just, they add in an extra term, which it's like if you have a function f of x1, x2, and x3, maybe it's equal to x1 plus x1, x2 plus x3 plus x2 squared, or something like that, right? Some function of these 3 variables, right? And then if you want to add like a constant term, you can, maybe do that. That's what this extra variable actually does. It's like a constant term. It doesn't matter. Just ignore it for now, and maybe we'll talk about it later. But it's just a kind of like a constant term. Okay, so it gives the model a little bit more flexibility. Okay, then the weights, which are all arbitrarily assigned, although he did manage to keep them all less than 1, right? The weights are all less than 1. We said we wanted them to be. Actually, these are a little bigger than the ones we said we wanted to be, but okay, so those are the weights. Okay, now we want to propagate the error backwards, and let's take a break and come back to this. Okay, because this next part is going to be a little bit dry. So let's take a break. So, okay, so where are we leaving this at this moment? What question are we trying to solve?
How to adjust the error.
Yeah, how to adjust the W's, right? Okay, so this notation and my presentation here gets a little bit dry. So let's take a break. Keep that in your mind as what we want to do. Take a break, get ready for a bit of dryness. Okay, so net J here just means the input into node J. I'm sorry. Sorry about that. Sorry, can you see it now? Okay, so net J here just means the input into node J. So here they have, for example, Let me just fix this. Here they have net A, which would mean what? The input into node A. Let's check that picture again. So here's node A. So if they write net A, it means what's coming into here. Okay? So what's coming into here? It's actually, well, sorry, it's this plus that, right? Okay. So that's what happens. What's coming into net A? It's that stuff that we just said. Turns out that for this data, it's going to give us 1.32. Okay? That's okay. Okay, how does the neural network learn? It propagates the error backwards. As each observation from the training set is processed through the network, an output value is produced from the output node. That's what we've been saying. Assuming that we have only one output node, which that's what we've been saying. Okay, and then we use something called, this output value is then compared to the actual value. Okay, I said that at least 10 times already, of the target value for this training set observation. And the error, the actual minus the output, is calculated. This prediction error is analogous to the residuals in regression models. To measure how well the output prediction fits the actual target values, most neural network models use the sum of squared errors. How many people have studied regression before? Nobody. Okay, that's what I thought. Okay, anyway, regression is some other technique in statistics. And anyway, the question is, how do we measure the error? So you'd say, what do you mean, how do we measure the error? We just said that the error was no, we didn't say that, but we've already measured the error, right? We already said, how do we measure? The simple answer to how we measure the error is the actual minus the output, right? What the actual value was minus our output. By the way, this is a little bit confusing word. By the output, they mean the prediction, our prediction, versus the real number, the real data number. So that's what they mean by actual versus minus output. The output is what we predict, the actual is what the actual number actually was. Okay, is that clear? So we just calculate that difference. So what do you say? What do you mean? How do we calculate the error? It's obviously just this, right? But they're talking about, okay, so we did that for one set of data. We ran one set of data through our neural network. We get an actual minus the output. But then we run another and another and another and another. If we run 10 through, then we're going to get a whole bunch of actuals and outputs, right? How do we combine them, is what they mean. So here's how we combine them. We sum up the difference of them, and we square each of those. Now you might say, why in the world should you square those? And that's that comes from regression, they square them. I don't know, there's just a lot of reasons why you might want to square them. You don't have to square them. It's not like this is not a hard and fast rule. This is the formula we decide to use. Okay? You don't have to square them if you don't want to. But the problem is, the one problem that squaring gets rid of minus signs, right? And if you leave the minus signs in there, you'll get sort of cancellation. And if you get cancellation, we don't want to do that. We don't want to allow cancellation to happen. Because sometimes that'll bring it down to 0, right? Because you'll get positives and negatives, bring it down to 0, and that'll be misrepresenting the error. Because you'll be saying the error was 0 when it wasn't 0. So that's just a very quick way to explain it. But anyway, one thing that squaring does is it does get rid of the cancellation. Okay, and that's something we want to get rid of. So that's one reason to use the square. Now, this is confusing here, because it says sigma over all the output nodes. And what's that mean? Well, that should be confusing, because you should say, wait a second, we only have one output node. That's right. So in this case, we don't need that sigma. But they're being general. They're saying, suppose we had 6 output nodes. Now, we haven't seen anything like that. You don't know exactly why we would want something like that, but we might. And in that case, you have to do something like this as well. Okay, but in our case, don't get confused. Just throw this out. Okay, so you're just summing over all the records, which is what we said. We're going to run one set of records through there, then another set of records, another, and then sum them up, sum this stuff up with the squares. Okay? So it's just a formula, and it's not even 100% clear. We don't have to use this formula, but we want to be able to sum up the errors somehow. Okay, so it's called SSE, that means the sum of the squares of the errors. The sum of the squares of the error. So that's what we're doing. We're squaring the error and summing it. Another notation is, I'm sorry, that's not wrong. That's wrong. Okay, the problem therefore is to construct a set of model weights that will minimize the SSE. Right? That's what we want to do. We want to minimize this SSE, because this is called our error function. The SSE is our error function. Now, this looks kind of simple here, especially if you just ignore the second sigma here. It's pretty simple, right? Just summing actual minus output. But if you think about it, this part is not simple, the output. Because the output is our prediction, right? And we just said that our prediction is horribly messy, actually. Right? This is our prediction function, and it's horribly messy where it comes from. So there's a horribly messy thing in here, in the output. But in fact, it's just an actual number. But where it comes from is a horribly messy thing. Okay? But yeah, we just get an actual number, so it's not messy at all. But inside there, we could say there's a big mess. Okay? So, and that is our error function. Okay? Everyone follow? That's our error function. The problem, therefore, is to construct a set of model weights that will minimize this error. In this way, the weights are analogous to the parameters of a regression model. Well, you haven't studied that, so maybe this is not good to mention, but the true values for the weights that will minimize SSE are unknown. Now, what do they mean by that? So in regression, you have something like this. You have some data. So here's, let's say, give me an example here. I want to predict somebody's weight, and I use I want to predict somebody's height, and I use their weight. So I have W there and H there. Okay? So this person is really pretty short, and their height is not too much. And this person, their height is quite high. I'm sorry, their weight is quite high, and their weight is here. We get another person here, and another person here, and another person here, and another person there. Right? So we have that problem, that situation. Now we want to say, what's the relationship between height and weight? Well, one thing we can obviously say is that when the weight increases, we expect that the height will also increase according to this picture. Right? As weight increases, I mean, if we look as a person gets fatter, they don't get taller. That's not what I mean. I'm talking about if we look at different people and this person is heavier than this person, we kind of expect them to be a bit taller. It's obviously not always true, but we might get data like this, and that suggests that what? As W increases, H also increases. And I could ask you, what's the relationship between them? And that's like a regression question. And the answer in a regression answer would be, oh, that's the relation. Okay, there's maybe we say there's a straight line relationship, or maybe you don't want to say, maybe you say there's a kind of curve relationship. Anyway, we'll say there's a straight line relationship. Anyway, now, are any of my dots actually on there? No. So none of the dots are actually on there, right? So, but that doesn't mean that the model isn't like the best straight line model we can have, right? The best straight line model you have is the one that sort of fits this data as best as possible, right? And then we say there's some error in this model. For example, here's error, right? And here's error, and here's error. So we can sum up all that error and call that the error of the model, right? And then you say, oh, okay, well, how about if I thought of a different model? Like this one. Maybe that's a better model. In other words, if I take the error off of the blue line, maybe that's less than the error off of the green line, right? And we want to choose the line which has the least error, right? And by the way, this is exactly what we mean by the sum of the errors. You sum up these errors, but the problem is if you sum those up, you're going to get cancellation. And so it doesn't really work. So instead of just summing them, we take the square of this plus the square of this plus the square of that. That's how they do it, to avoid the cancellation. Yes?
What is this cancellation?
You know, cancellation means this is like maybe +3 error, and this is -1 error, and this is -2, right? The distance, it's just the distance. So when you sum those up, you get cancellation, right? And so actually, you're going to probably get 0 as the sum of the errors for both the green and the blue. So that doesn't help me choose the lines, right? So the cancellation just makes it useless. So we square it instead. And that's exactly what we do here. Even though we're not talking about line here, but we do exactly the same thing. Okay? So anyway, now, the thing is, this is called regression. And in regression, if you give me a set of dots, a set of those blue data points, I can tell you which line is best. There's a calculus formula that you use, and you just put it into Excel, and it tells you right away which line is the best line in terms of this criteria. So there's a simple way to do it. It's called in mathematics, there's a closed form for it, for minimizing the error. There's a formula for it. Closed form just means there's a formula for it. Okay? However, in the case of neural networks, there is no closed form. There's no formula to tell you, oh, this is the best set of weights to choose. Right? Here, there is a formula to tell you, this is the best line to use. But in neural networks, there's no formula for that. I don't know what weights to use. Here, what I mean by best line is what, really? A line looks like, what's the equation of a line in general? You either write it as y equals ax plus b, that's one way to write the equation of a line, or you can write it like this. How do they do it? They write it like this, a1x plus a2y plus a3 equals 0. That's a general form for the equation of a line. Okay? So what do we do? What do I mean? Here's the best line. When I tell you here's the best line, I'm just saying, what are these values? A1, A2, and A3. Those are just like the weights in the neural network thing. So I can tell you what these are, but I can't tell you what the W's are because there's no formula for neural networks. There's no, like here, it's very simple. You just do it in Excel, it'll tell you right away what line to use. That means when it says what line, it's telling you what the A and the B are, or what the A1, A2, and A3 are. It just tells you. So that's like telling you the weights, but you can't do that for neural networks. Okay, get it? So, then we're stuck. So we don't know how to get the best model when it's a neural network. So that's what it says. However, due to the nonlinear nature of the sigmoid function permeating the network, it's everywhere in that, we said it was a horrible mess, and there's a whole lot of sigma functions in there, there exists no closed form solution for minimizing SSE as it does for the least squares or for the regression. For the regression there is one, but here there isn't. What time is it? 44. We still have a second. Okay, so we use something called, it comes from optimization theory. It's called the gradient descent method. And it's pretty cool, actually. It's pretty cool. And it relies on the derivative. How many people have studied calculus? Derivatives? Derivatives means this thing. Yeah, you have, right? Everybody has, right? So what does that mean? That means, that tells you what? That means if you have a curve, it tells you the slope of the curve, right? That's what that does, right? So, like that, or like that, right? It tells you the slope. That's all it does. That's the whole thing. Okay? But this is pretty cool, and it uses the slope. The slope of what? Well, first of all, what we want is, what's our goal? Our goal is to minimize SSE. Right? We want to minimize the error. That's minimizing SSE. Okay, somehow. Now remember, SSE was equal to sigma output minus output minus actual, right? But remember that output, I just told you, is a horrible, messy thing in the whole formula for it, right? But there's a formula for it. In other words, this SSE is actually a function, right? This is a function. So we can talk about taking the derivative of that function, because you take derivatives of functions, right? And this is actually a horrible function, but it's a function, right? So I could say, take the derivative, and I have to have a variable down here, maybe let's say x1 or something. I can talk about the derivative of that, right? Now, if you, I don't know, has anybody studied this notation? Something like that. Partial derivatives. Have you studied that or not? So that's like when you have a function in two variables. So this is a function in one variable, one input variable, right? But you might have a function in two input variables. That means you have another axis coming out here. So you have an axis here and an axis here and then a height above there. So this height might be z as a function of x and y, right? So you have, this is the x-axis, this is the y-axis coming out. So you have x, y, you get a point over here. You say, how high is the function above there? It's up here. Somewhere else it's over here, somewhere else it's over here, somewhere, right? So you get this surface, right? Like an umbrella, the top of an umbrella, right? So then you can say, oh, if I'm walking in this direction, that means you're slicing that umbrella like this, right? That means you're getting a curve, right? You can say, how does it change when I go in this direction? Well, on the other hand, you can say, if I'm walking in this direction, then you get a different curve. And you can say, how does it change when I'm going in this direction? And that's what I mean by the partial of z when I go in the x direction, and the derivative of z when I go in the y direction. Right? That's what those mean. And those are relatively easy, because when you go in this direction, you just have a single curve like that. So you can do the derivative of that. And you go in this direction, you can imagine finding the derivative of something like that. Those are just single curves. We know what they mean. Okay? So anyway, so here's the idea. Think of this. We only have a few seconds. We're trying to minimize what? The SSE. So imagine a surface that describes the SSE. Okay? Let's say it's a two-variable inputs, just like x and y, and you have the SSE curve up here, right? So like one of the inputs is the first input into the neural network, and the second, let's say we have a neural network with just two inputs, right? And then blah, 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 like over here, right? So you only have two inputs. So you have like an X input and a Y input, okay? That's what I'm talking about. And I want to minimize, I think that's what I'm talking about, and I want to minimize, maybe not, but anyway, and I want to, so I have this surface. Let's imagine we only have a surface in 2 dimensions, in 3 dimensions. But really we can do this for many inputs, but just imagine now. Okay, here I am, here. This is the surface of my error function. I want to do what? I want to minimize it, but I don't know how to do it. So I'm sitting up here at some point. The question is, which direction do I go? It's like you're a blind person on a mountain. Okay? Here's the mountain, and I'm standing on it, on the mountain, and I want to get down, and you're blind. How do you know where to go? Right? So probably you're not going to walk up. You might say, okay, now if I walk up, I might get up, and maybe the lowest point is over here, so maybe it's better to walk up. But if you're completely blind and you don't have any knowledge of what's really true, you don't do that, even though it might be wrong. Right? Maybe if you want to get home, or you want to get to the ocean is actually down here, and if you walk this way, you're not walking towards the ocean. That's going to be a mistake, but you don't know how to avoid that. You can't avoid that. Okay? So what do you do in general? And basically, what do you have to do? You choose the direction which has the greatest slope downward. That's called the gradient descent method. Okay, so I'm not going to walk up, and I'm not going to walk in this direction where I don't go down at all. I don't go up or down, and I just kind of stay at the same height. I'm going to walk this way. And that's called the gradient descent method. Okay? And we do that, and that's what we're doing. We look at the derivatives, because what does the derivative tell you? The derivative tells you the slope. So you walk basically down. You walk in the direction with the greatest derivative. Okay, now if you haven't studied this kind of stuff, then it's a little hard to go into detail about that. But that's the idea. So you but if you just do it in one, so this is the general form. So it means that this is the partial derivative with respect to weight 1, weight 2, weight 3. I made a mistake. It's not the x, y inputs, it's the weights. I said over here, that's not really right. We're taking the derivative with respect to the weights. But anyway, let me just keep going. Okay, here's a one-dimensional input example which illustrates this idea. So this is the best weight, the true weight, the weight you really would like to find. Okay? In other words, here's the error. This axis is the error. Where is the error lowest? Right here, right? So you'd like to find that, but you don't know it. Okay? You have an arbitrary weight W, which is like over here. But one thing you can do is you can take the derivative right here. If you take the derivative right here, you find that the slope is like this, right? So in that case, obviously, what's the correct direction to walk? Obviously, the correct direction to walk is here, right? Because if your W is here, and this is the best W, you'd want to walk this way. But and what does the derivative say? Is the slope positive or negative here? It's increasing. This is increasing here, right? So the slope is positive. How about here? Is the slope positive or negative? It's negative, right? So when the slope is negative, what's the correct direction to walk? To the right. When the slope is positive, what's the correct direction to walk? To the left. So that's the way it works. You take the derivative, And if the derivative is positive, you want to decrease your weight, the weight that you got. The question is by how much, you don't know that yet, but at least you know you want to decrease it. If the derivative is positive, what do you want to do? You want to increase your weight. So you want to look at the derivative and move in the direction of the negative of that number. So in other words, you don't move forward, you move backward. Here, you don't move backward, you move forward, right? Okay? So, that's the idea. So the question is, how much should you change W by? Right, that's the question. Here's W. What direction should I change it? This way or this way? From the picture I know that I want to go this way. If I calculate the derivative, it's positive, then positive derivative must mean that you want to decrease W, and negative derivative must mean you want to increase. So we'll check the derivative. And here. So we look at the sign of the derivative and we take it negative, and that's what we want to add to to the current value. So if this is our current value, I look at the derivative here, it's positive. If I take the opposite of that, that's how much that's what I want to add to this to get closer to this. Right? Does that make sense or not? Okay? That's the idea of using the gradient descent method. Okay, now as I said, if you don't know this kind of notation, I could spend a whole lecture talking about this, and then maybe we could go on from there. I don't know if it's worth doing that or not. I could do it, but how many people want to see that in the next lecture? Nobody. I'll ask one more time. How many people want to see that in the next lecture about partial derivatives? This symbol here means we're talking about partial derivatives. Or is what I've just said so far kind of enough? Not enough. Okay. Well, we could do that. It's not really data mining, but it obviously plays a role here. So here's the thing. I have a current value for W, which is here, and I want to adjust it to a new value. And the question is, how much should I add to it, or what should I add to it? And the answer is, when it's up here, when it's to the right of this, I want to add a negative number, and when it's to the left of that, I want to add a positive number, and the derivative, the sign of the derivative, will tell me should I add a positive number or a negative number, right? That's the idea. Now, we still have no idea of how much to add, right? We only said that we know whether we should add a positive or a negative number, but not how much. But this is helping us to adjust our W's, okay? And we still have to work on how to... so what do we have left here to figure out? How much to add. We've decided that we know whether we should add a positive or a negative amount, but we don't know how much. Well, let me just give you a quick clue about that. And that is, we're going to use the degree of slope here, how much slope there is, as a kind of starting point in terms of how much. So here, suppose I had a W right here. What's the slope here compared to the slope here? Is the slope here higher or lower than the slope here? Lower, right? So if I follow what I just suggested, then I'm going to subtract less if I have here than if I'm here. Both times I'm going to subtract, because both times the slope is positive. We said we're going to take the negative of the slope. So I'm going to add negative numbers in both cases to this value. But how much of it, how big of a negative number, I'm gonna add a bigger negative number when I'm here, because the slope is more positive here than here. Do you understand that idea? That's the basic idea. Okay? And that is expressed somewhere here. Basically here. Okay. Well, we have to stop, so I'll stop now. So I ask that you review the last 10 minutes of our class before you come to class next time. And the way you can review the last 10 minutes is I'll post this video. Wait. Yeah. I think I'm still recording, yeah. So you just review the last 10 minutes, then we can start from there. Okay? So I'll ask that you do that. And I think everybody knows that these videos are at, that's my publisher name on YouTube. So you can find it, I'll put it there. Okay? I hope. As long as nobody's coming now.